Our project is called Brainstorm.Photo. The main problem we are trying to solve is a lack of brain MRI images due to their lack of variety in its datasets. We are feeding generative AI, specifically a generative adversarial network, brain MRI samples to create synthetic datasets for MRI scans of the brain that can be used for medical research, disease diagnosis, and future machine learning.
A generative adversarial network, or GAN, is a type of neural network designed for generating samples that resemble a given dataset. A GAN consists of two neural networks that are trained simultaneously, the generator and discriminator. The generator is trained to produce mimic data that can fool the discriminator. The discriminator then receives both the real and mimicked datasets and attempts to distinguish real and fake data. These results are relayed back to the generator, and this whole process improves the generator's ability to produce realistic datasets and the discriminator's ability to detect fake samples. In our case, we repeated this cycle until a satisfied brain MRI was generated.
So in our code, we have three main data classes that we focus on. So for the MRI dataset, this is a custom dataset in the PyTorch that is designed to load and pre-process MRI images from a specific directory. So in this one, it focuses on grayscaling the data set we put in and rescaling it so it has consistency when we load it. This is a generated class we created. This class takes in random noise as input and generates the fake MRI images. The goal of this class is to produce an image in a sizing of 128 by 128 with transposed layers for better image clarity. Now this is our discriminated class. This class determines whether an input image is fake or real. This is important later on when we are training the model because we want to aim to trick this model into believing that our generated images are real scans. Now these are just the parameters for the imaging. In addition, this is where we initialize the model and start training the data sets. Now this is the for loop, is the training model that we use. We set it to 1,000 iterations for our data set. This essentially goes through and determines the losses as each epoch is finished. This is the output of the training. You can see that with each epoch, there's a discriminator and a generated loss. The losses are really important to follow because it shows how well the model is performing during the training. Ideally, the discriminator loss should be lower and the generated loss should be higher because at the beginning because it's struggling to trick the discriminator. However, eventually they should start evening out later on, as you can see. And as you can see, we also coded it where every 100 epoch, they post an image of our MRI scans to see how the process is going currently.
Okay, so this is a Figma mockup for how our program would look like. So if you click Generate MRI Scan, then it'll go to an interface of a blank MRI scan with some tools that would help in the AI generation. So for example, we would have patient details, which would list specific attributes that a patient would have in order to help with the accuracy of the image. We also have the Insert tab, which would be used to insert the type of disorder. We also have the Change View tab, which would show the top, side, and front views of the MRI scan. We have the Generation tab, which would change the image resolution and the amount of images that the AI would generate, which both affect the image accuracy. And lastly, we have the color coding tool to show where the disorder is located. When everything is all set up, when a run button is pressed, the tool is able to generate an MRI scan from the specifications that were given from multiple images. Eventually, it will generate a final image, which will represent the MRI scan for what is generated based off of the specifications.